Is it working? Yeah, perfect. Okay. Okay, whatever. So, hi everyone. So, I'm going to start with the query evaluation problem, which is the following. You're given a query and a database, and the goal is to compute the set of solutions. So, here we have a query written in first-order logic, for example. Our databases will always be relational structures in these talks. So here, some nodes and edges and some colors of node. And the set of solution is just a set of tuples. Okay. The problem is that even for small databases, not too big databases and some really small queries, the set of solution can be gigantic. And this leads to two difficulties. The first one, for practical reason, we don't want to have a huge set of solutions. We cannot display it, we cannot store it, we cannot do anything with that. And often we will only use few solutions. And for theoretical reasons, the problem is that the time needed to compute this set of solutions does not reflect the hardness of the problem. Because sometimes the problem is really easy, and we just spend a lot of time just writing the outputs. And we don't want to do that. So I'm going to talk now about another problem, which is query enumeration. Here we still have a database and a query as inputs, but the goal is to compute solution one by one. So you first want a first solution, then a second solution, and so on. An enumeration algorithm will be divided into two steps. The first one is a pre-processing that will help us to speed up the enumeration phase. So in this first step, you're allowed to do some pre-computation. You can compute pointers, new colors, anything you want. And ideally, it will only take time linear in the size of the database. When the pre-processing is done, you've built what we call an index, and then you can start the second step. Using the index, you will produce solution one by one at a time, a first solution, a second solution, and so on. And the delay is the time between two consecutive outputs. So what we want is a linear delay, a linear pre-processing followed by a constant delay. And we talk about constant delay enumeration after linear pre-processing. Okay. So to be sure that we are all on the same page, I'm giving a quick example. So here the database is a set of nodes from 1 to n, and we also have a set of edges. And the query is looking for pair xy, such that xy is not an edge in the database. So a naive idea would be to go through every possible pair of nodes and just check whether it is an edge or not. If it's an edge, don't output it. If it's not an edge, it's a solution, and then you can output it. The problem is that you can have big packs of consecutive edges, and so the delay will not be constant. So what do? We have linear preprocessing. So during that time, we will build those blue arrows that directly jump to the next solution. So we do that starting by the bottom. So is there a solution after nn or there are not? So we point to null, and then we go up. So let's consider the case of ij plus 1. When we want to find the next solution after ij plus 1, we look at ij plus 2. Is ij plus 2 a solution? The answer is yes, because it's not an edge. So ij plus 1 points to ij plus 2, and we continue to go up. So now we look to ij. When looking at ij, we look at ij plus 1. Is it a solution or not? In that case, ij plus 1 is not a solution, so we cannot point to ij plus 1. But ij plus 1 already points to ij plus 2, so we can directly jump to ij plus 2. Okay. This is the end of the preprocessing. It took only linear time because we did only a small thing per each for each edge. And now how do we enumerate the solution? We start with the first possible tuple, 1, 1. We check whether it is a solution or not. In that case, it is not a solution. So we have these blue arrows that point to 1, 3. We output it, then go to the next tuple, 1, 4. Is it a solution or not? It is a solution, we output it. 1, 5, we output it. 1, 6, not a solution. We go to 2, 4, and we continue. Okay, so this query can be enumerated over any structures. But it is not always the case. Let's look at these queries. It's looking for pair of node x and y that have a common neighbor. And here it's way more complicated, because if we can see that it is actually encoding the Boolean matrix multiplication. X, Y is the solution if only X there is a Z, such that X is related to Z, Z is related to Y. So this is the Boolean matrix multiplication. So what will happen if we have an algorithm to enumerate efficiently this query? This will compute exactly the Boolean matrix multiplication. So we would first start with a linear preprocessing. So linear here is linear in the size of the input, so n squared, because the matrix have n squared elements. Then you enumerate the solutions. There are almost n squared number of solutions. So in n times n squared, we have computed the results of the matrix multiplication. And there are conjectures saying that there are no such algorithms. So this query cannot be enumerated with constant delay over any structure. So we'll need to put some restriction either on queries or on database. And we'll have to put really important restriction because this query is really simple. It's an acyclic conjunctive queries. So we need to go even deeper. So for example, assume that now D is not any kind of database, but it's a tree. What can we do? Then it's become a lot easier because we only have several cases to study. Given a node X, some solution, well, one solution might be its grandfather. You need to check whether this is a solution or not. We also have to check its grandchildren, are they a solution or not, and its siblings. And all of those solutions seems quite easy to enumerate. So this is an example of restriction. And the question is what kind of restriction has been used by the past to get constant delay enumeration. So some work has been done in the following setting. We don't want to put any restriction in the database parts. What query will be enumerated efficiently? And as I just mentioned, it's not working for acyclic conjunctive queries. We have to go deeper. So a strict subset of acyclic conjunctive queries, which is free connects. It has been mentioned like 5 minutes ago. Another setting is you want to work with highly expressive queries, like MSO queries. And here we'll have to put really huge restriction on the database part of the input, and it will only work for trees and graph with bounded queries. And the third part is what happens if we look at first-order queries, which is what I'm going to present. So before mentioning the restriction, we'll link the enumeration problem to other problems and see for those problems what are the good restrictions that have been used. So the model checking problem is the problem of given a Boolean query and a database decide whether this is true or not. Ideally, we want to solve that in linear time. We have the enumeration problem. The evaluation problem, the goal is to compute the entire set of solutions. The counting problem, the goal is to count how many solutions are there. And the testing problem is the following. You first do some preprocessing, ideally linear time. Then someone gives you a tuple, and you want to decide whether it is a solution or not, ideally in constant time. And when we look at those problems, we see that the model checking problem is the easiest one. So if you want to be able to enumerate, count, or test, you have to be able to do the model checking problem efficiently. And for FO queries, this is an AW star complete problem when there are no restrictions. So what kind of restriction has been used for the model checking problem? So here are lots of classes of graphs that have been used. So graph with bounded tree widths, planar graph with bounded degree, and it goes up to a more complicated structure like nowhere dense graphs. And nowhere dense graphs is the maximal class because if a class of graph is closed under subgraphs, there is a really sharp dichotomy saying that this class of graphs that is closed under subgraphs is either nowhere dense or somewhere dense. If it's nowhere dense, then we have an efficient algorithm. If it's somewhere dense, then the problem is again AW star complete. So we have this really, really sharp dichotomy. And so what about the enumeration problem? So we have algorithm for some smaller classes of graphs. And the question is, do we have the same dichotomy or not? And this is what we answer in our paper. So what are those nowhere dense graphs? I will not give the definition, which is not really easy to read, but just so example of classes of graphs that are nowhere dense. So any kind of bounded degree graphs, graphs with bounded tree widths, planar graphs, any classes that exclude a minor is nowhere dense. And this is a really robust notion. There are lots and lots of equivalent definition using asymptotic ratio of edges over vertices, so the notion of locally excluding a minor, and more recently a winning strategy for some two-player games. I will talk about that later. And so what are precisely our results? So over nowhere dense classes of graphs, every first-order queries after pseudo-linear pre-processing, we can enumerate the solution with constant delay, and we can test whether a given tuple is a solution in constant delay. The counting problem has also been solved, but not by us. It will be presented next session, tomorrow afternoon. Okay, so what is pseudo-linear? Because I said linear preprocessing and here pseudo-linear. So we do not have exactly linear preprocessing, but almost. So something is pseudo-linear if for every epsilon, as close to 0 as you want, there is a rank such that if our database is bigger than this rank, the running time is the size of the inputs to the 1 plus epsilon. If the database is smaller than this rank, then we can brute force because we have a small database. So for example, any n time polylog is a pseudo-linear running time, but if you have an exponent that is strictly bigger than 1, then we do not have a pseudo-linear preprocessing. Okay, so what are the different tools that we use? The first one is a really recent HAMF normal form for FO queries that has been introduced for the counting problem, will be presented tomorrow. Then we also need several things from the paper for the model checking problem by Grohe, Kreutzer, and Silberg. The first thing that we use is the algorithm for the model checking. We also use two of the tools, the neighborhood cover, I will talk about that in the next slide, and the game characterization of nowhere dense classes of graphs. And this is only, with that we can do the testing problem. For the enumeration problem, we have some extra work using some shortcut pointer. Really, it looks like the same. That's my first example about these pointers that skip a pack of consecutive edges. It's roughly the same. So briefly, what is a neighborhood cover? So we want to talk about neighborhood because first-order queries are local in some sense. But we cannot study every possible neighborhood because a neighborhood might have a linear size and there's a linear number of nodes. So we will have the sum of the size of each neighborhood is quadratic, and we want linear or pseudo-linear. So a neighborhood cover here is a set of bags such that for every node there is a bag that contains its neighborhood. Every bag is not too big. It's included in the bigger neighborhood of one node. And for a given node, the number of bags that contain it is not too big. Okay, so I will use that in a few seconds. But before that, what's the game characterization of nowhere dense graphs? So it's a two-player game, splitter and connector. Connector tries to preserve the graphs, and splitter tries to destroy it. We have two parameters, L and R. L is the number of rounds, and R is the radius of the game. So at every round, connector picks a node C, and we will restrict our attention to the R neighborhood of this node, and then splitter picks a node S, and we delete it. And we say that splitter wins if in less than L rounds the graph is empty. And so the theorem is that if our graph is in some nowhere dense classes, the number of rounds only depends on R and does not depend on the size of the graphs. And so this number of rounds that will only depend on R, the radius, and therefore only on the size of the query, will be an inductive parameter that will be used in our preprocessing algorithm. So I will just give an example of how do we use this neighborhood cover and this game for a specific queries. So this is a query we had trouble with before. So we are looking for pair of node X, Y that have a common neighbor. And so what do? We take A, we take the bag that contains its neighborhood, and then splitter deletes a node. So we have a new graph, and in this new graph, splitter wins with one less turn, because this is basically one turn of the game. But how does the query change? We have different cases. The first one is when A is far from the deleted node. The second one is when A is close to the deleted node, and the third one is when A is the deleted node, so when the node picked by splitter. And so how does the query change? In the first case, if A does not have anything to do with the node that has been deleted, then we still enumerate nodes that are at distance 2. They are still the only possible solution. In the second case, if A was connected to the deleted node, then we put in red every node that was connected to S, the deleted node, and we labeled in blue every node that is connected to a red node. And so if A is red, we enumerate every node that is at distance 2. Those are still valid solutions, but we also have to enumerate every red node because they were at distance 2 before. And last case, when A is deleted, then we will only enumerate the blue nodes. Okay, so I think this is it. So we have this sharp dichotomy for the enumerating problem and for the testing problem, just like the model checking one. But what works remains. The first part is that our dichotomy only works for classes of graphs that are closed under subgraphs, but there might be some dense graphs that still admit good properties, and so there are recent works and still many ongoing works. The second possible improvement of our work is enumeration with updates. So here we assume that we are in a scenario where we can enumerate the solution efficiently, but what happened if someone changed something in the database after we've built the index? Do we have to compute it from scratch all over again, or can we rebuild it in, let's say, logarithmic time or constant time? So there have been lots of work recently in previous pods and ICDT. One of them will be actually in 2 talks, and that's it. Thank you.
Can you give some intuition about lower dense databases?
Well, that's tough. So I don't think this notion can be used like in real life. I think it's just, the notion is just used for the dichotomy results, but essentially every nice classes falls way below, like trees, bounded degree, planar. I don't know if there are some instances that does not fall in any of those categories that are still narrow dense and that are used. So I don't know.
Do we gain anything on the upper bound by looking at amortized constant delay?
So I'm not sure I understand the question, but okay, so if we look at somewhat dense classes of graphs, even if we lose some constraint on the delay, it will still be hard, because if you can produce a first solution in polynomial time, then you show that AW star equals FPT. So I don't know what we can do.
Right, so I understand that in terms of the lower bound, we don't really gain anything. Even for matrix multiplication, the same reduction applies even if we look at amortized costs. But in terms of upper bound, we might gain something by relaxing the constraint.
Okay, I don't know. Maybe.
So in all this work that you cite, are there also some implementation efforts going on?
Okay, so let's go back a little bit. So I think that the work about the free-connex acyclic conjunctive queries, this is implementable, and it might have been implemented, actually. I don't know. For trees, there is the blow-up when you go from MSO queries to automaton, but if you start with an automaton, that might be implementable, I don't know. For FO queries, it's really difficult. So every time the first step is put everything in Gaffman normal form or UMF normal form, and this is really hard to do. Especially in our work, we do that several times because at each step of the induction, we rebuild a normal form. So yeah, I don't know if anything could be implemented in this area. Yeah.
What is it known about this dichotomy for fragments of the FO?
For fragments of FO, so for any kind of database, we have a dichotomy, like free-connex acyclic conjunctive queries.
No, this dichotomy about nowhere versus somewhere there is a class, right?
So what is the question then?
Yeah, what if you restrict to some subclasses of first order queries?
Like just conjunctive queries with, yeah.
Bounded numbers.
So there are some results about conjunctive queries over X underbar structures, I think. So this is like XML with axis relation. There are some works where we have a linear delay. I'm not well aware of that part, but yeah, there might be something about conjunctive queries, not free-connex acyclic, more powerful, and yeah, some other classes.